Hello everyone. In the previous videos we have learnt how to find out the value of a determinant and its application in two-dimensional coordinate geometry. In this video we will learn about the properties of determinants. The first property here is if the rows and columns of a determinant are interchanged, then the value of determinant remains unchanged. We know the meaning of interchanging the rows and columns. It means making the transpose of a matrix or a determinant. So here we can also remember this particular property as that the value of a determinant and the value of its transpose are equal. It means we can say that the determinant A is same as determinant of A dash. For example, we can learn it by a numerical value. Suppose we have a determinant delta and this is 2, 3, 1, 5, 4, 6, 4, 3, 2. We know how to find out the value of this by expansion. We are expanding it about row 1, then the value of this comes as 2 into 8 minus 18 minus 3 into 10 minus 24 plus 1 into 15 minus 16, and this is 2 into minus 10 minus 3 into minus 14 plus minus 1. If we simplify, this comes as minus 20 plus 42 minus 1. 42 minus 21 is 21. It means the value of this determinant is 21. Now if we interchange the rows and columns, means we are taking delta dash, then it comes as 2, 3, 1, 5, 4, 6, 4, 3, 2. Now if we expand it along row 1 only, of course we know that the value of a determinant can be found out by expanding it along the rows or along the columns. Any row or any column. So here also, if this is the determinant and we are finding the value, expanding it about the column, we will find the same value because the row has become the column here. But even then, if we expand it about row 1, let's see the value. This comes as 2 into 8 minus 18 minus 5 into 6 minus 3 plus 4 into 18 minus 4. We have already learned how to find out the value by expansion method. Simplifying this, we are getting 2 into minus 10 minus 5 into 3 plus 4 into 14. Is it coming as minus 20 minus 15 plus 56, and you can see here this is 35. 56 minus 35 is equal to 21. So we are getting delta is same as delta dash. So we can remember this, that the value of the determinant and by interchanging the rows and columns of it are equal. The second property is that if we interchange any two rows or any two columns, then the numerical value of the determinant remains unchanged, but the sign changes. If the value of the determinant is positive k, then the value of the determinant after interchanging any two rows columns will be minus k. Let's see this with the example. We have one of the determinant delta. The elements in this are 2, 1, 3, 3, 6, 5, 5, 4, 4 row wise, and after finding the value of this expanding along row 1, we are finding this is minus 33. If we interchange its two rows, row 1 and row 2, we can also write it symbolically as R1 interchanged with R2. Then suppose we are getting this as delta 1. If we find its value expanding along row 1, we are finding this as 3 into 4 minus 12 minus 6 into 8 minus 15 plus 5 into 8 minus 5. Simplifying this, we get 3 into minus 8 minus 6 into minus 7 plus 5 into 3. This is minus 24 plus 42 plus 15. You can see here, this is 42 plus 15 is 57 minus 24, this comes as 33. This was minus 33, this is 33. So can we say that delta 1 is equal to minus delta? Similarly, if we interchange any of the two columns and find the values, we will find that the numerical value remains same, only the sign of the value changes. The third property is that if any two rows or any two columns of a determinant are identical, then the value of determinant is 0. The meaning of identical is that either two rows or columns are equal or one is some multiple of the other. Let's understand this by some example. Suppose the first example we are taking, delta is 2, 3, 5, 4, 7, 1, 2, 3, 5. In this determinant we are finding that row 1 and row 3 are equal. Row 1 is equal to row 3. Let's see the value of it. If we expand it along row 1, it will be 2 into 35 minus 3. Minus 3 into 20 minus 2. Plus 5 into 12 minus 14. Simplifying, we get 2 into 35 minus 3, that is 32. Minus 3 into 18 plus 5 into minus 2. We get here 32 into 2, 64, minus 18 into 3, 54, minus 2 into 5, minus 10. Is it 64 minus 64 equal to 0? It means if any two rows or columns are equal, then the value of the determinant will be 0. Let's take one more example, the delta 1. In this we are finding the elements are 2, 3, 4, 5, 2, 10, 1, 6, 2. In this we are finding that third column is twice of the first column. 2 into 2, 4, 5 into 2, 10, 1 into 2, 2. Expanding it along row 1, we get 2 into 4 minus 60. Minus 3 into 10 minus 10. And plus 4 into 30 minus 2. Simplifying this, we get 2 into minus 56 minus 3 into 0 plus 4 into 28. This is equal to minus 112 minus 0 plus 112, which is equal to 0. So we are finding if any two rows or columns of a determinant are identical, then the value of the determinant is 0. The fourth property is if each element of a row or a column of a determinant delta is multiplied by some constant, that is suppose k, then the value of the determinant also will be a multiple of k. Let's understand this by example. That is, suppose a determinant is given to us. The elements in this are 2, 1, 3, 3, 6, 5, 5, 4, 7 in the rows. We expand it along row 1 and find that its value is minus 6. Now if we multiply every element of column 1 by k, we get this delta 1. Every element of this column 1 has been multiplied by k. Then if we find the value by expanding along row 1, this will be 2k into 42 minus 20 minus 1 into 21k minus 25k plus 3 into 12k minus 30k, and this comes as 2k into 22 minus 1 into minus 4k plus 3 into minus 18k. This gives us 44k plus 4k minus 54k. Is it also coming as minus 6k? So we are finding that delta 1 is equal to k into delta. The same property can be used to take some number common from any of the row or any of the column of a determinant. How we can apply this fourth property in taking something common? Let's understand it here by taking one of the determinant, that is having the elements in column 1, 3, 5, 8. In the second column it is 4, 7, 1, and the third column it is 14, 21, 35. We are finding in the third column every number is multiple of 7. So we can take 7 common from C3 and we can write this as 7 into 3, 5, 8, 4, 7, 1, and this will be 7 2 ja 14, 7 3 ja 21, 7 5 ja 35. The value of both will be same. It means if we are finding any number common in any of the row or any of the column, that can be taken as common as a multiple of the value of the determinant. The same property we can also apply in understanding some of the metrics. Suppose we have a matrix of order n into n. Let A be a matrix of order n into n. And if we multiply an element k to the matrix A, then we know it is to be multiplied to every element of it. It means what we will find that the value of determinant of k into A will be equal to k to the power n into determinant A. We can understand it easily by taking some of the matrix of order 2 into 2. Let A be a matrix of order 2 into 2. Suppose that is A is equal to A, B, C, D. We know the value of determinant A. That will be A, B, C, D. The value is A into D minus B into C. Now suppose we multiply this matrix by K. K into A will be, we have to multiply K to every element of it, that is K into A, K into B, K into C, K into D. If we find the value of determinant of this, it means determinant K into A will be determinant K into A, K into B, K into C, and K into D. Do we find that K is common from first row as well as from the second row, or from the first column and from the second column? And if we apply the fourth property, we can take K common from the first column and from the second column, or from the first row and from the second row. We will get K into K into determinant A, B, C, D. Is it equal to K square into determinant A or not? Also, if we have A as the matrix of order 3 into 3, if A is the matrix of order 3 into 3, and then we multiply K to it and find the value of determinant of K into A, determinant K into A will be equal to K cube into determinant A. And by understanding this, we can follow this as the rule that if A is a matrix of order n into n, then the value of determinant of K into A will be equal to K power n into determinant A. The fifth property is that if each element of a row or a column of a determinant is represented as the sum of two numbers, then the determinant can be represented as the sum of two determinants, that is by splitting that particular row or column. How it is? Let's see. Suppose we have a determinant delta and the elements in this are A, B, C, D plus X, E plus Y, F plus Z, and this is G, H, G. Then this determinant can be represented as a sum of two determinants, that is delta 1 and delta 2, where we find that delta 1 is equal to A, B, C, D, E, F and G, H, G. One of the number of this has been taken here in the second column. And delta 2 is equal to A, B, C, X, Y, Z, G, H, G. It means we are taking the second number as the second column of it here. This property can also be used to find the sum of two or more determinants. We can't add the determinants like we are adding the matrices, that we can add the corresponding elements. But the determinants can be added in case we find that two of the rows or columns of them are same and only the third row or column are different. Suppose we have a determinant delta 1 in that the elements are P, Q, R, S, T, U, V, W, X. Another determinant delta 2 is having the elements P, Q, R, S, T, U, A, B, C. What we find? In delta 1 and delta 2 we are finding first column and the second columns are same. Only the third columns are different. It means we can add these two determinants. We can write delta 1 plus delta 2 is equal to P, Q, R, S, T, U. The first and second column will remain same. The corresponding elements of the third columns will be added. That will be V plus A, W plus B and X plus C. So this can be taken in any of the row or any of the columns. If we are finding the elements are different, then we can find the sum of the determinants, that may be two or more determinants. The sixth property is that if some multiple of a row or a column of a determinant is added to some other row or column of that, then the value of determinant remains unchanged. It means if we multiply every element of one of the row or column of a determinant by some particular number and add it to some other row or column, then the value of the determinant is same. There is no change in that. See here, suppose we have a determinant delta. Elements in this are A, B, C, D, E, F, G, H, G column wise. If we perform the operation in this, that we are adding k times of C2 in C1, applying in C1 plus k into C2, then this determinant delta, suppose it becomes delta 1. Will it be A plus k into D, B plus k into E, C plus k into F or not? The second and third column remain same. We can verify this property numerically or theoretically. Suppose we want to verify it theoretically here. See, from the fifth property, what we have, if this is represented as sum of two numbers, then this can be represented as a sum of two determinants. So can we write this delta 1 as A, B, C, D, E, F, G, H, G plus K into D, K into E, K into F, D, E, F, G, H, G. Is it same as delta? It is delta plus Are we finding k common from this first column? If we take k common, it is DEF, GHJ. Do we find here in this particular determinant that first column and second column are same? C1 is equal to C2. Therefore, the value of this will be 0. So, we can say it is delta plus 0 or equal to delta. So, if we multiply the elements of a row or a column of a determinant by some number and add it to any other row or column, then the value of the determinant remains unchanged. These are the main 6 properties of the determinants, but some more properties can be added to the list. Like here we have, if all the elements of a row or column of a determinant are 0, then the value of determinant is 0. Like delta, all the elements of first column are 0. In delta 1, all the elements of the second row are 0. The value of this is 0. Of course, we can understand it easily because we know that we expand the determinant either along with a row or with a column. If we expand along the column, because each element is 0, so the value will come as 0. Here, if we expand it along the second row, the value will automatically be 0. One more property we can add to it, that is for any two square matrices A and B of the same order, determinant of A into B is same as the determinant of A into determinant of B. To understand this, suppose we have two matrices A and B here. Can we find the value of determinant A here? Determinant A is 2, 3, 5, 1, that is 2 minus 15, or we can say minus 13. Determinant B, that is 5, 4, 7, 2, that is 10 minus 28, or we can say minus 18. If we find the value of determinant A into determinant B, that is minus 13 into minus 18. This is 234. Let's find the value of A into B. We know how to multiply the matrices. This is 2, 5, 3, 1 into 5, 4, 7, 2. So we find the value of the matrix as 2, 5 the 10 plus 35, 2, 4 the 8 plus 10, 3, 5 the 15 plus 7, and 3, 4 the 12 plus 2. This is 45, 18, 22 and 14. If we find the value of determinant AB, that will be 45, 18, 22, 14, or you can say 45 into 14 minus 18 into 22, which is equal to 630 minus 396, and this is coming as 234. So do we find that determinant A into B is equal to determinant A into determinant B? In the next video, we will learn about minors, cofactors and the adjoint of a matrix. Thanks for watching my video. If you have any comments or doubts, leave them in the comment box and I will get back to you.